This is a sunburst chart, and it is probably the most admired chart that almost nobody can read. People call it beautiful, then scroll past because they cannot say what question it answers. Here is the honest version. Every ring is one level deeper into a hierarchy. Every slice angle is its share of the whole. The center is everything taken together. This one is a single project folder, 136 gigabytes of disk. By the end, you will read one of these, prepare data that will not lie inside one, and know when a different chart is better. Forget the circle, because the circle is the last step. Underneath every sunburst, there is a plain tree, one root, some branches, and leaves at the ends. Here is that folder as an indented outline, which is the shape your file system already has. Notice where the numbers live. Only leaves carry a measured size. A folder carries no number of its own because it is worth the sum of everything inside it. That rule is what makes the chart add up later. Now lay that outline on its side and give the whole tree one strip of space. The root takes the entire width. Its 4 children split that width in proportion to their sizes, and their children split each of those in turn, level by level. That is a partition. Every node gets a start, an end, and a depth, and a parent's children exactly fill it without overflowing. Drawn flat, this is already a real chart in its own right, called an icicle chart, and it is genuinely useful on its own. Here is the move most tutorials skip. Bend that strip until its 2 ends meet. The strip's total width becomes the circumference of the small circle in the middle. Each bar's share of the width becomes the same share of the turn, and each row becomes a ring. Watch as it bends. Nothing is recalculated, nothing is resorted, nothing moves relative to its neighbors. Only the reading of the 2 coordinates changed, which is why the correct name for this chart is a radial partition rather than a ring of pies. Read a single slice properly. Take training images out on the 3rd ring. Its distance from the center tells you one thing, how deep it sits. It says nothing about size. What tells you size is the angle it sweeps, and this one covers about 14% of the turn, so it is about 14% of the disk. The slice's visible area, though, is not the encoding at all. Outer rings are longer, so 2 slices with identical angles cover very different amounts of screen, and we will come back to why that matters. People call this nested pie charts, and that does real damage because it suggests each ring is an independent breakdown drawn around the last one. It is not. Every slice sits entirely inside its parent's angular span and can never straddle 2 parents. Watch the previews folder on the outside. Its parent sits directly beneath it, and that parent's parent beneath that, all the way to the middle. Reading inward recovers the complete path back to the root, which is the one thing a pie chart can never offer. Hierarchical data arrives in one of 2 shapes. The first is nested, a root object with a children array and values on the ends. That is what a well-behaved interface returns, and the layout consumes it directly. The second is an adjacency list, a flat table where every row carries its own identifier and its parents. That is what a database query returns, and it is the shape of every organization chart. Neither is better. Both must become the same tree before any coordinate is computed. Turning that tree into a chart takes 4 steps. First, you build the hierarchy, which wraps your data so every node knows its parent and children. Second, you sum, and this is the important one. A node with children contributes nothing of its own, so every folder total comes from the leaves beneath it. Third, you sort the siblings, which fixes the order the arcs appear in around the circle. Fourth, you run the partition, the only step that produces coordinates. The partition gives every node exactly 4 numbers, and tutorials name them without explaining them. The first pair is a start and an end along the axis being divided. Treat the whole axis as one unit of space. A node owning a quarter of the data gets a quarter of that span, positioned wherever its parent sits. The second pair is the depth band, which says which level the node lives on. Feed the first pair into an angle, and you have a sunburst. Into a horizontal position, and you have an icicle. Here is the mistake that ships most often, and it never announces itself. Suppose your data gives folders their own reported size as well as their children. If your summing step adds both, every folder is counted once for itself and once through its contents. The total inflates. Inner rings stop matching outer ones, and the chart still renders perfectly. On the left, the middle claims far more disk than the machine has. On the right, folders contribute nothing of their own. 4 kinds of bad row will get past you. A leaf whose value is 0 becomes an arc of 0 width, present in the data, invisible on screen. Here, the migration guide has no pages at all, and that gap is exactly what somebody needed to see. A missing value behaves identically, so an absent field and a real 0 become indistinguishable. A negative cannot become an angle, so excluding it makes the printed total stop matching your source. And 2 siblings sharing the name read as one category and are 2 arcs. Here is the question that quietly ruins hierarchy charts. A share of what? Every angle is a fraction, and a fraction needs a denominator. Global normalization keeps the whole hierarchy as the denominator, so an arc is its share of everything at every depth. Subtree normalization picks one branch and opens it to the full circle, so angles become shares of that branch. Watch the center as I focus on compute. The arcs keep their relationships, and every percentage has changed meaning. Sibling order looks cosmetic and is not, because a viewer reads movement as meaning. Sort by value alone, and any 2 siblings with the same value can swap between renders, so an animated chart shows arcs sliding past each other when nothing has changed. Add a second key, usually the name, and the ordering becomes total. Identical data always draws identically. Keep whatever order your query returned, and the layout becomes a property of your database's mood rather than a property of your data. This is the perceptual tax you pay for the circle, and you should charge it consciously. Angle is the encoding, but area is what your eye adds up, and area grows with distance from the center. 2 slices with the same angle, one on the second ring and one on the fourth, carry the same share and cover very different amounts of screen. Humans also compare angles well when adjacent and badly across a circle. When precision is the job, print the number or draw a bar. Depth is the knob most people get wrong because adding a level feels free. Every ring you add makes every ring thinner, and thickness decides whether a level can hold a label at all. Unbalanced trees make it worse. One branch reaches 4 levels and another stops at 2, so you pay for depth you barely use. A hairline of angular padding and a little corner rounding separate neighbors without borders. But the real fix is folding the deepest level into its parent, where its magnitude still counts. Color here has one job worth doing, telling the reader which arcs are family. Give every branch at the first level its own hue, and let each descendant inherit it, varying only lightness outward. A sequential ramp is the other honest option, but only when color encodes a second measure, such as age or error rate, and then it must replace branch identity rather than fight it. The common failure is a rainbow per slice, which destroys ancestry and fails a color vision check at the same time. Labeling separates good sunbursts from screenshots. A tangential label runs along the arc and needs arc length. A radial label runs outward and needs ring thickness, flipping on the left half so it never reads upside down. A horizontal label needs both. Whichever you pick, measure the real string against the real space first, because the failure is silent. Text renders, gets cut at the slice edge, and looks like a deliberate abbreviation. Below some minimum angle, nothing fits, and a leader line is the answer. Two things decide whether your chart survives real readers. The first is size. Most people meet it on a phone at roughly a third of this width, so the chart must resize from one source of geometry, rather than from fixed pixel values, and every label that fails small may as well not exist. The second is that some readers will not see it at all, and some have asked their device not to animate. For those, the indented outline and the finished still frame are the answer. Cost allocation is the case this chart was built to answer. Here is 1 month of cloud spend, about $106,000, split by service family and then by service. The question is not what any line costs. Your billing console already answers it. The question is where the money went. Watch the rings arrive. Compute takes nearly 2/3 of the circle, and inside it, training alone is more than half. A finance conversation just became an engineering one. A product catalog is a hierarchy whether anyone drew it or not, and analytics supplies the magnitudes. Here is 1 week of sessions across an outdoor equipment storefront. The 4 branches at the first level are close to even, which sounds boring and is useful because it pushes the story out to the second ring. Focus on climbing. It is the smallest product branch, and yet climbing shoes alone draw more sessions than the entire service branch, which is not something anyone spots in a table of 30 rows. Bundle size is a part of a whole measured against a hard budget, which is exactly what this chart encodes. 605 kilobytes of minified JavaScript attributed to the module that produced it. The largest branch is your own application code, which is the healthy answer. But the single largest leaf is not in the biggest branch. One framework package accounts for 132 kilobytes on its own, more than the whole charting branch and more than every polyfill combined. Coverage is a hierarchy where the interesting arcs are the small ones, which inverts how you read the picture. 320 documentation pages. Reference dominates, and it should, because reference is generated from code, and guides are written by hand. So ignore the big wedge and look at guides. Deployment is healthy. Security has 4 pages for a subject that deserves far more, and migration has none, so it has no arc at all. Absence has no geometry, which is why empty categories must be printed in text beside the circle. Now a case where the hierarchy is real and the chart is wrong. Taxonomy is the textbook example of nested data, so people reach for a sunburst constantly. These are approximate counts of described animal species by phylum and class. Arthropods are somewhere around 87% of the total, and insects account for most of them. The result is a circle that is one wedge, with every other phylum crushed into a margin no label can fit. The data is right, and the picture is still useless, so a bar chart on a logarithmic scale respects the reader more. Here is the exercise worth doing before you commit. Take your data, write the exact question, and draw it 6 ways. 1 tree, 1 question. Which 2 categories get homepage space? Sorted bars win outright because ranking wants one shared axis. The sunburst is second and earns it by showing the shape of the whole while keeping ancestry visible. The icicle is the same partition with room for labels. The tree map uses its rectangle fully. The tree and the packed circles answer structure and containment instead. 3 questions look hierarchical and are not. The first is flow. If a thing can arrive at a stage from several places, it has more than one parent, and a partition gives every node exactly one slice inside exactly one parent. That is a Sankey diagram. The second is change over time. A circle has no time axis, and 12 sunbursts in a row ask for the hardest comparison there is, so draw lines. The third is a network, where cycles mean there is no root and no partition to compute. Here are 9 ways this chart fails in production, and the reason to name them is that 8 of the 9 render perfectly. Too many tiny arcs, so outer rings become texture. Too much depth, so the most specific level is the least readable. A rainbow palette, so color stops meaning family. Internal values counted twice, so the total lies. Unstable ordering, so the animation reports news that did not happen. Labels clipped at the slice edge, which look deliberate. Gratuitous rotation, which blocks every comparison while it runs. A network forced into rings, and comparing 2 arcs on opposite sides of the circle. On the web, this chart earns its keep through interaction. Hover a slice, its ancestor path lights, a tooltip gives the exact number, a breadcrumb says where you are, and search or a filter cuts the tree down to the part you asked about. In a video, nobody has a cursor, and faking a pointer is worse than not trying. So author it as motion. Dim everything. Light one wedge, print its real number, hold it long enough to read, then release. Drilling down is the interaction people love and implement carelessly. Zooming into a branch does not magnify anything, it changes the denominator. The branch becomes the new whole, and every percentage silently changes meaning, so the zoom and the relabel must happen in the same frame. Watch the center as outdoor opens. It stops saying 100,000 sessions and starts saying 40,000, because that is what the angles now divide. A zoom with no visible way back to the root is a trap. Motion is worth the effort exactly when it changes what the viewer understands. 4 moves earn their place. Revealing ring by ring turns depth into a sequence instead of a wall of color. Wrapping the icicle into the circle is the explanation itself, so show it once. Dimming and lighting an ancestor path puts attention exactly where the spoken sentence has gone. And landing on a still frame and holding it matters, because reading a chart takes several seconds, and the final state is what gets remembered. Every motion in this section has a name, and the name is the interface. A preset takes the finished layout and the current progress and hands back geometry, which means a reviewer can ask what a chart is about to do before a single frame is rendered. The alternative is what most decks accumulate: a scatter of durations and delays tuned by eye on one slide and copied to the next, where nobody can say what any of them mean. Naming them also lets a preset carry its own list of risks, and lets the ones that lie be registered so they can be refused. Start with the 2 baselines. The first is no motion at all, the finished chart on the first frame, and every animation you write has to beat it. The second is a plain fade, which is also what a reader who has asked their device to reduce motion must receive. Then the sweeps. Sweeping the turn once tells the viewer that the whole circle is one quantity being spent, rather than a shape that happens to be round. Growing outward from the center says something different. Depth is radial, so the hierarchy arrives before any number does. Reversing either one is legitimate, but direction is a convention you fix once and then keep, because two identical datasets drawn in opposite directions look like different data. A cascade is a stagger with a rule behind it, and the rule is the lesson. Cascading by ring turns depth into a sequence the eye can follow. Cascading by branch completes one wedge before starting the next, which is how a person actually reads a single path from the root outward. Staggering by value puts the largest arc first, so the answer to what dominates arrives before any of the detail. Staggering in preorder is the only one of these where a parent can never trail its own child onto the screen, which matters because a child appearing before the thing that contains it is a small lie told very fast. Notice what none of them do. Not one of them animates a per arc angle. They move opacity, and they move radius, and every angle is final from the first frame it is visible. The construction entrances build the chart in visible stages. Outline, then fill, then labels is three phases the eye can follow, and it makes one rule impossible to miss. A label must never lead its own arc. If the name arrives first, the viewer reads a claim about a shape that is not on screen yet. The wedge wipe and the aperture both work because each moves exactly one limit, one angle, or one radius applied to every arc at once. A single shared limit cannot put a child past a parent that was clipped to the same limit, so containment holds by construction rather than by luck. The quiet ones matter too. A fade says nothing about structure, which is sometimes exactly right, and it is the fallback every other preset settles into. Every one of these renders perfectly, which is the problem. A chart that never holds still can never be read, so continuous rotation and the wobbling kaleidoscope are out on that ground alone. Exploding the wedges apart breaks the one property that makes a partition legible, which is that the parts stay adjacent. The tunnel zoom spends its whole entrance too small to read. The most interesting failure is the elastic one, and it is a lesson about easing. Ease a radius, or an opacity, with an overshooting curve, and nothing is harmed. Ease an angle with the same curve, and every arc briefly claims more of the turn than it owns. A child spills past the edge of its parent, and the chart states a number that appears nowhere in the data. Cubic curves stay inside 0 to 1. Elastic and back curves do not, and angles are exactly where that matters. An update is only an update if the chart can tell which old arc became which new arc, and that decision is the join. Join on the node's identity, its full path from the root, and an insert animates the arc that actually changed. Join on the array index, and inserting one row at the top makes every arc animate into its neighbor's place, which looks like the entire dataset moved. Arrivals and departures need care of their own. A new leaf that pops in at full width is indistinguishable from a reorder, so it enters at 0 width and grows into its slot. A departing leaf shrinks to nothing rather than disappearing between two frames, and the whole branch arriving has to open as one piece, its children keeping their proportions inside it. Because a child on screen without its parent is a shape with no denominator. Structural changes are where the join earns its keep. Move a subtree to a new parent, and the identity has to survive, or the chart shows a deletion followed by an unrelated insertion. Resorting is the interesting case because it changes nothing about the data at all. Watch the resort cell and you can see why it needs care. Interpolate straight between two different orderings, and the ring tears open in the middle of the transition, so for a full second, the chart draws a total that is not the sum of anything. Every other update here holds the earlier order for exactly that reason. Filtering is the one that misleads quietly. Remove the small rows, and the denominator moves, so every percentage the viewer just read is now wrong, and the chart owes them a sentence that says which total they are looking at. Time turns a chart into a sequence of states, and most of the rules carry over unchanged. A time step is an update, so it joins on identity, and it lands on a still frame. A streaming update needs an explicit cue, because a chart that changes while the reader is mid-sentence has changed the answer without telling them. The case worth naming is the one where the two states share no denominator, which happens whenever the totals are not comparable. There is no honest tween between those, because every intermediate frame would be a mixture of two different wholes. The correct answer is to stop animating and put the two charts side by side, and the cell here says so on screen rather than quietly interpolating anyway. A sunburst without interaction is a picture. With interaction, it becomes a way to ask questions, and each of these is a different question. Hovering makes one arc the subject and, importantly, moves nothing else. Lighting the ancestor path answers what this is a part of, in one gesture, without the viewer having to trace rings inward by eye. A tooltip exists to give the exact number that an angle can only approximate, so it has to actually carry a number. A breadcrumb records how you arrived, which is only useful if it stays on screen after the pointer has gone. And a pin is the difference between a chart you can point at and a chart you can read. It lets the pointer leave without losing the state it selected. Here is the same click, answered three ways, so the choice can be made on evidence. The first lights the path from the clicked arc back to the center and leaves every other arc untouched. The second dims everything that is not on that path. The third drills, making the clicked branch the new whole. All three answer the question. They differ in what they take away. Lighting the path takes nothing away, so the viewer can still compare the highlighted arc against its neighbors, and that is why it is the one to reach for first. Dimming is stronger and costs the comparison, which is a fair trade when the chart is dense. Drilling is the strongest and the most expensive because it changes the denominator, and a chart whose denominator moved without saying so is a chart that lied. Navigation is where a sunburst stops being one chart and becomes a series of them. Drilling into a branch makes that branch the whole, and the number in the middle has to change with it, because otherwise the viewer keeps reading the old denominator against the new picture. Watch the center in the semantic zoom cell. The name and the total both change, and that is the entire difference between a semantic zoom and a camera zoom. A camera zoom makes things bigger. A semantic zoom changes what the chart is about. Every drill also needs a visible way back, or the chart is a one-way door, and depth is a control the reader can turn rather than a constant you chose for them. The last group is the one that decides whether the chart is usable rather than merely impressive. Search has to find every match and then step through them in an order the viewer can predict. Arrow keys have to move through the tree because a chart that only answers a pointer excludes everyone using a keyboard. Multi-select holds 2 or 3 arcs together for a comparison the eye genuinely cannot make across a circle. Every state has to be reachable, leavable, and shareable, which in practice means it lives in the address bar. And the reduced motion path is not a reduced feature set. Every state change still happens, and every state is still reachable. What gets removed is the travel between them, not the destinations. The circle is a default, not a requirement. Half a turn is still a complete partition, and it fits the wide frame that most screens actually are, while having how crowded the labels get. Drawing the root as a visible disk states the whole before any part of it, at the cost of radius the rings wanted. A large hollow center is worth its radius when the whole is doing work, holding the total and the breadcrumb, and wasteful when the whole sits empty. Ring thickness deserves the most care. Equal thickness for every level is the honest default, because unequal thickness reads as unequal importance whether you meant it or not, and a reader has no way to know that you widened a ring only to fit its labels. Labels and color are where most sunbursts are won or lost. Each orientation has a different budget. A radial label gets the ring's thickness, a tangential one gets the arc's width, and a horizontal one gets whichever is smaller. Measure before you place, and when a name does not fit, a call-out with a leader line is its honest home. Never shrink type until it fits, because the reader cannot read it either. Color is the strictest rule here. A hue can carry ancestry, so that every descendant of one branch shares a family, or it can carry one measure, so that hue means magnitude. It cannot do both, because the moment hue means two things, the viewer has no way to know which one they are looking at. These are all good charts. None of them is a sunburst, and confusing them is the most common way this chart gets misread. A stack of pies renormalizes every ring to a full turn, so a slice in the outer ring has no parent at all, and you can see the rings disagree. A polar bar chart uses equal slices and puts the magnitude in the radius, which is exactly the opposite convention, and the two look alike enough to swap by accident. A radial tree carries structure and no magnitude whatsoever. Chord and Sankey diagrams both show flow between categories, and a Sankey allows a node to have two parents, which a partition cannot represent at all. The test that separates them is simple. In a radial partition, and only in a radial partition, every child is contained by its parent, and the parts of a level sum exactly to the level inside it. Two implementation rules carry most of the weight. The first is keying. Every arc needs an identity that survives a data update, and its array position is not 1. Insert a row at the top, and every key shifts, so the framework animates the wrong arc into the wrong place. Use the node's full path from the root. The second rule is that the frame number is the only input to animation. There are no timers, no interval callbacks, and no animation state anywhere in the render. Charts are usually tested by screenshot, which reports that something changed and never says what. Geometry has invariants you can state exactly. Every angle and radius is finite and never negative. Every arc ends at or after it starts. No child escapes its parent's span, which is the defining property of a partition. Children sum to their parent within tolerance, which catches double counting. Every drawn label actually fit, and its text is the complete authored string. An empty tree and a tree whose total is 0 both still produce valid output. Let us put the whole video into one edit. On the left is a chart that renders without a single error and communicates nothing. 4 rings of equal thickness, a color per slice, no padding, a tiny hole, and no labels because none would fit. 4 changes fix it. Fold the deepest ring into its parent, and note the total does not move. Give each branch a hue its descendants inherit. Add a hairline of padding and measure each label against its real space. Here is the whole thing as a checklist you can run before you ship. Is your data a real tree? 1 parent per node and no cycles? If not, you need a different diagram, not a different palette. Do only leaves carry values? And does one branch add up by hand to what the center claims? Is the denominator printed? And does it change when someone zooms? Are you at 3 rings or fewer? Was every label measured at phone width before it was drawn? This is the chart we started with, and it should look different now. Rings are depth, and angles are share. The center is the whole, and the label in the middle names it. The wedge that stands out is media, and inside it, the finished renders, which is a specific thing to go and delete. The lesson is smaller than the chart. The outline is the data, and the circle is one reading of it. Draw your next hierarchy as bars, as an icicle, and as a tree map first.